Well, good morning. My name is John Darlington. I'd like to talk to you about SoCLabs, a global community based around projects on the ARM ecosystem. I'll also be introducing some of my colleagues, Daniel Newbrook, who will help me with the workshop. Unfortunately, David Flynn couldn't be here today. But also you're going to hear from a whole collection of the community that engage in projects around the world. And part of our workshop today is to introduce not only SoCLabs as a concept, but to introduce the sort of academic groups that are working within it. So I'll take you through a short introduction to SoCLabs, and then Becky from ARM is going to come up and talk about ARM academic access and how that enables the community in the ecosystem. Daniel is going to then take us through the main part of the workshop, where we will discuss some of our reference designs that help enable academics to quickly take SoC designs from concept all the way through to tape out. And we'll intermix the education on that with practical examples of projects from around the community that we initiated back in DATE24. And then finally, we'll talk about the plans for our contest for this year coming up, which will run from DATE25 to DATE26. And then hopefully some people in the room will take part in the contest and come back in a year and tell us their results. So what is SoCLabs? As we say, it's a global academic community for system on chip based around the ARM architecture. And our aim is to make the whole process of taking your SoC design from its initial concept right through to tape out. What we'd really like to do is expand the number of academic institutions that can do this. So I am lucky, I come from the University of Southampton. We've had an 18-year relationship with ARM. I think we've taped out 15, 16 times with them. And you have to understand it's a privileged position to be in. And what we're keen to do is to encourage more institutions to get involved, and ARM have been very generous to the community by providing all of their IP into the academic community free of charge. But fundamentally what we need to do after that is obviously improve academic output, and what we're keen to do is to get more ASIC designs into Tier 1 publications, which is our primary output as academia. So in order to do that, what we really need to do is promote best practice in SoC design and bring in both the best experience from academia but also from industry, and then spread that amongst the community. And we think one of the best ways to do that is to enable design reuse, both in terms of the fundamental SoC design, but also in terms of all of the other aspects you need to actually create design in terms of workflows and just managing projects. We are well supported by ARM, the EDA community, and a growing number of people within the semiconductor industry that are aimed at trying to improve the whole experience of SoC design within academia. So in a moment, Becky's going to come up and talk about ARM academic access and how things have changed in terms of when I started, in terms of having to build, a quite complex way to get things taped out, and also to work with ARM to get the IP so that I could tape out. ARM academic access now, it's freely available. Becky will talk about how easy it is to sign up. We've really simplified the process to do that over the years. But I'll just finish off my talk about some of the remaining difficulties and how we overcome them for academics to do tape outs. So what we do is we take the core compute infrastructure that ARM provide, that is the same infrastructure that their industrial partners do, like our Apple, to take those all the way through to tape out. But what we've done is enhance those with specific IP that really targets the academic need and looks at some of the things that are slightly different between industrial use and academic use. That's allowed us to create these what are called reusable reference designs. And those reusable reference designs start out with very simple processor designs like the M0 microcontroller and go all the way up through to A-class designs such as those in your mobile phone. Also, we focus on the design flows and specifically the back-end design flows where academia struggle. Sometimes we just manage to get it into an FPGA and actually taking it all the way through to tape out is something that we need to build on in terms of skills and experience and share within the community. Another sort of weakness within academia is we're not very good at producing verification assets. In industry, a lot of the activity is around building the verification assets you need to ensure that your tape out is successful. So a lot of the time, academia is focused on the design side, and so by improving the verification assets and sharing those amongst the community, we should be able to get tape outs achieved more efficiently. And then finally, we need to build ways of communicating all that to people across the globe. So part of the problem is the integration challenge. So each of the providers that you need to actually get a SoC taped out, they're all very helpful. So ARM's very helpful with IP. The EDA tool vendors are very helpful with their tools. And also you need to get PDKs and technology from the foundry partners. But the difficulty is it's usually left both in industrial settings and also in academia settings to integrate that all into a process by which we can get a tape out completed. And in academia, we tend to start from scratch each time we run a project. When you're in industry, the products tend to develop in a fairly progressive way. And so they reuse a lot of the infrastructure from one product to a next product. And so I think reuse in the project environment as well as in the technology is a key to making progress. So one of the things we've looked at is the whole way you set up and establish a project, the way you do maintain your source code, and these are all things that industry does very well and that we need to replicate in industry. And if we can bring those industry best practices into academia, then we stand a better chance of getting our SoCs through to tape out more efficiently. Another thing that you learn as you go out into industry is how to manage projects and how to get them through to the end. And what we try to do is instrumentalize that project management by putting milestones that you can then follow as an academic. And if you follow through those workflow steps, you'll get to a successful tape out. These are types of activities that are quite unfamiliar to the academic world and especially to new researchers. So the more we can do to share those, the better. The other thing that industry works on really well is knowing that you've got experienced engineers you can go and talk to if you're a new engineer. And you don't tend to find that in academia. So PhD students, for example, will struggle, even if they're talking to their own academic, to how they access the skills they need. And so what we want to do is share that experience across the community. So we've got great examples of projects that we're working on where they share their experiences, how much area something is, how this particular problem in the design flow has caused them an issue, how long it takes to actually to do a particular stage. The only way you can estimate projects is with experience. And if you can't have that experience, then the best thing is to look at other people's experiences and use that as a guide. So the key thing is to share not only the technical information, but actually all the project management information as you go along. So what we need is not necessarily more open source, but more open projects. So in terms of the actual sort of IP, one of the things we struggle with in academia is transitioning from the FPGA environment through to a full ASIC. And what we've done is we've looked at that problem and produced reference designs and workflows that help transition that from the FPGA through to the full ASIC flow. And Daniel's going to talk about NanoSoC later, which is our entry-level system, and how that can be easily used to create custom accelerators for AI and ML, or other examples are adding front ends for sensors. And what we've done to help support the debug environment and really support just for you to focus on your core research. One of the other things we've done is looked at power, and again, one way that the industry looks at power is to say we need the most efficient ASIC. In academia, what we're more interested in is benchmarking against our peers. So how do we get out really efficient information about the energy consumption of our custom accelerator? So again, in NanoSoC, we've looked at the power domains, not from ultimate efficiency, but from how you can get effective measurement. And those effective measurements coming out will allow us to get our academic results published in Peer 1 publications. So Daniel will take through NanoSoC. I want to just cover the cost issues. Some people say, cost of tape outs is quite significant. So we've looked at NanoSoC, and you can build a full SoC with a custom accelerator. We've got quite a few examples. You're probably only testing a kernel. You're not testing a massive complex video processing system, which we'll talk about in the second half, using an A-class processor. But we've got a couple of examples where it's only 1 millimeter by 1.5 millimeters. And you can take that out via Europractice for under €5,000. And the whole package, including the board, etc., and packaging, is less than €10,000. And it's a very cost-effective way to get master students or PS students into SoC design. Of course, as you want to sort of express up the pathway, then if you went into a car rental, you can obviously get hold of a, subcompact. If you only need a small car, but if you need more performance, then you'll get a bigger car, a family car, and maybe you'll get a top end. So we've again looked at that and produced reference designs for each of those academic spaces in terms of how much of an academic team you can put together, how much capital you can put together towards the tape out, and also the requirements you need, whether you're doing simple things like vibration sensing, handling voice, or whether you're actually trying to do real-time video processing. So these are all available on SoCLabs, and you're going to hear about them in the workshop later. To support that, you need to take your SoC design through a whole set of steps, and we've mapped all those steps out on the SoCLabs site, and you can follow them through each of the high-level stages from your original product design all the way through to tape out and then post-tape out testing. So where have we got to? So we have about 90 universities globally taking part in SoCLabs in 22 countries. We have about 20 projects ongoing at the moment. We've taped out a number of those using technology such as the 65 nanometer TSMC node. We currently have 2 designs in physical, which we hope to tape out fairly soon at 28 nanometers. And we have a plan to tape out on 16 nanometers during the on the November shuttle this year. Finally, I'd like to thank everyone that's in the Semiconductor Education Alliance. One of the great things in working in SoCLabs is working with both academia and also the semiconductor industry. And I'm now going to ask Becky to come up and talk about ARM academic access. Hi, Becky.
Hi, thanks very much, John.